Hello everyone, welcome to my channel. In this video we are going to be talking about Euler path, Euler circuit, Fleury's algorithm for Eulerian path. So first we are going to be talking about what is an Euler path and Euler circuit, then what is an Euler graph, then after that conditions we need to have an Euler path or a Euler circuit. Then after that we are going to see how we can print an existing Euler path or a circuit. There is an algorithm for that called Fleury's algorithm. Then we will see how this Fleury's algorithm works. Then after that we are going to be implementing this Fleury's algorithm in Java. So first let's see what is an Euler path and a Euler circuit. So now we will see what is a Euler path and a Euler cycle. Euler path is a cycle that visits each edge in a graph exactly once. So then if the starting and the end vertex in the cycle is same, then that is going to be called as an Euler circuit, which is going to be a closed Euler path. This Euler circuit is also an Euler path, but it is going to be closed because it starts and ends at the same vertex. Here let's see in this example, here in this left cycle I'm going to first start at E, then go to D, then go to C, then go to B, then go to A, then go to C. Here I have started at E and ended at the C vertex. This is going to be an Euler path. Here in this right side example, I'm also going to start at E, then go to D, then go to C, then go to A, then go to B, then go to C, then I am coming back to E. Here you can see in these two examples I have used all the existing edges, and in this one I have started at vertex E, ended at vertex C. In this right side example I have started at vertex E, ended at also vertex C. This is going to be an Euler cycle, also known as Euler circuit. So then we will see what is an Euler graph. Now we will see what is an Euler graph. An Eulerian graph is a graph that's containing an Euler cycle or Euler circuit. And if it is going to contain an Euler path, it is going to be known as a semi-Eulerian graph. So I have taken the previous two examples again, and I'm going to again start at vertex C. Here you have to always consider that in a semi-Eulerian graph we have to always start at an vertex that's going to contain an odd degree. So here we can't start at an vertex that's containing an even degree. We can't start at here. You can see this B vertex is containing an degree 2. We can't start at that vertex. We have to start at vertex E, which is going to be containing an 1 degree, which is odd, or vertex C, which is containing an degree 3, which is odd. So again I am going to start at vertex E, go to D, go to C, then again go to B, then go to A, then come back to C. I have visited all the edges exactly once. So E, D, C, B, A, C. Here starting and the ending vertex is not the same. This is an Euler path. So this is going to be an semi-Eulerian graph. Then I am going to come back to this right side example. In this, all the degrees are even. We can start at any vertex. First, I am going to start at vertex A, then go to B, then go to C, then go to E, then go to D, then go to C, then come back to A again. Here you can see I have visited all the edges exactly once, and I have started then ended at the same vertex. This is going to be an Euler cycle or a Euler circuit. Then this graph containing an Euler cycle or Euler circuit, it is going to be an Eulerian graph. Okay, now we will see what are the conditions we need to have an Euler path or a Euler cycle. So now we will see what are the conditions we need to have an Euler path or a cycle. So first, in order to have an Euler path or a circuit, as the base condition we need to have all vertices with non-zero degree should be connected to a single component. So what's that mean? So let's take here, I'm gonna draw this small graph. Here all these vertices have an degree of 1. They are not 0, but they are not connected to a single component. This graph is disconnected. Here A and B are the connected ones. After that there is no any other edge to go to C or D. So this does not contain a Euler path or a Euler circuit. Then to have an Euler path, we need to have exactly 0 or 2 vertices which have an odd degree. So here this 0 is because Euler circuit is also an Euler path. That's why it is here 0 or 2. Then for to have an Euler circuit, all the vertices should have an odd degree. No, all the vertices should have an even degree. Here, as in the previous two examples I have taken, we can first calculate the degrees. Here in this the degree is 1, here the degree is 2, here the degree is 3, here the degree is 2, here the degree is 2. Here you can see there are 2 vertices that have an odd degree. So this condition proves true. So this contains an Euler path. Here, then after that, in this right side example, I am also going to calculate the degrees. Here contains 2, here the degree is 2, here in C the degree is 1, 2, 3, 4, here the degree is 2, here also the degree is 2. In this, all the vertices have an even degree. So this contains an Euler circuit. So those are the conditions we need to have an Euler path or a circuit. I have in the previous examples I have traversed this graph the way we need to have an Euler path or circuit. Now we will see what if we want to print this Euler path or circuit, how we can do that. There is an algorithm for that called Fleury's algorithm. So now we will see how this Fleury's algorithm works. now we will see how we can print a Euler path or a circuit. To do that, we have an algorithm called Fleury's algorithm. So first, here in these functions, first what we are going to do is, when we are going to run this algorithm, first we are going to check whether the given graph is Eulerian or not. How we can do that? By taking the number of degree in each vertices. If the number of degree in each vertex is 0 or 2, then that graph is Eulerian. Then we can continue with these functions. If it's not, then these functions stops. So first, as the first vertex, first we are going to take the first odd degree vertex, or if there are no any odd degree vertex, we are going to take any random even degree vertex. So here I have taken this graph as the example for this Euler path V. Here as the first vertex, we can see the degree of each vertices in this graph is even. So we can take any random even degree vertex. I am going to take A as the starting vertex. Here, Euler path V, I am going to take A vertex as the starting vertex. For each AV of V, that means for each adjacent vertex of this taken vertex. Here, as the vertex, I have taken A. There are two adjacent vertex for A vertex, which is B and C. So for each adjacent vertex, we are going to run this function, and in this function, we are going to check whether this is a valid next edge as the next vertex for this function. It is going to return true if AV is the only adjacent vertex of V, or if there are multiple edges and VAV edge is not a bridge. What is a bridge? A bridge is an edge. If we remove it, the graph becomes disconnected. So bridge is going to be used only when it is necessary. So if not, we are not going to use it. So first, I have taken A. For each adjacent vertex of A, I am first going to take B as the adjacent vertex. A, B as the adjacent vertex for this is valid next stage. Checking whether this B is the only adjacent vertex of A. Here it is not true because A has two adjacent vertex B and C, so it is not true. Then going to the second condition, if there are multiple edges and BA edge is not a bridge. Here you can see if we remove this bridge, the graph doesn't become disconnected. So this edge is not a bridge. So this becomes true. So it is a valid next edge. So first we are going to print this edge since this becomes true. A, B. We are going to print this. Then we are going to remove this edge. I have removed it. Then for the function again, I am going to take the adjacent vertex. So this is going to be D. So that is taken. Then as the vertex we have taken B. For each adjacent vertex of B, here you can see for each adjacent vertex of B, A is not a 1 because we have removed this edge. A is not connected. C is the only adjacent vertex available for B. So here as the adjacent vertex, I am going to take C. Here adjacent vertex is the only vertex of B. Here B, only adjacent vertex is C. So this is going to return true, and we are going to print that edge B to C. Then we are going to remove that edge. Then going to go to the function again with C vertex. Here taking C. For each adjacent vertex of C, here you can see there are A, E and D vertices available as adjacent vertices for C. So first we are going to take A as the adjacent vertex of C. We are going to check whether that is going to be a next valid edge or not. Here C, A. C A. We are going to check whether this is the only adjacent vertex for C. It is not. There are two other adjacent vertices. Then checking whether if there are multiple edges and CA is not a bridge. Here you can see, if we remove this bridge, this graph becomes disconnected. We have no any other way to reach this A vertex. So this is a bridge edge and we are not going to use it. So this becomes false. Then after that, we are going to go again for another adjacent vertex of C. It is going to be DOE. I am going to take D. Here it is C. Here I am going to take D. So for D, we are going to check if it is the only adjacent vertex of C. It is not. If it is a bridge edge or not. Here you can see, if we remove this edge, the graph doesn't become disconnected, so we can take it as the valid next edge. So first we are going to print that edge C to D. We are going to remove it. Then we are going to take D as the next vertex. Then for each adjacent vertex of D, here E is the adjacent vertex of D. We are going to take it to this function. D adjacent vertex as E. D adjacent vertex as E. Check whether E is the only adjacent vertex of E. Here you can see, since this edge is removed, E is the only adjacent vertex of D. So this is going to return true. So after returning true, we are going to print that edge D and E. Then we are going to remove that edge. Then we are going to go back to that function again with the adjacent vertex of D, which is E. Then after that, we are going to go for each adjacent vertex of E. Here there is adjacent vertex C. Going to go here, adjacent vertex is C for E. Checking whether C is the only adjacent vertex of E. Here you can see these edges are removed. So E is the only adjacent vertex of, so C is the only adjacent vertex of E. So this is going to return true. After returning true, we are going to print that edge. I'm going to print here E to C. Then we are going to remove that edge. Then for this function again, we are going to call C as the adjacent vertex. Here again C. Then for each adjacent vertex of C. So as the adjacent vertex, only A vertex is available. So we are taking that. C adjacent vertex A. Here A is the only adjacent vertex of C. It is true since all these edges are removed. A is the only adjacent vertex of C. So it is going to return true. Then after that we are going to print that edge. After that we are going to remove it. Then as the next vertex we have taken A, which is adjacent vertex of C. Here we have taken A. So for each adjacent vertex of A, here you can see all these edges are removed. There are no any other adjacent vertices available for A. So these follow stops. Then after that, finally, we are getting the Euler path or the Euler circuit available for the given graph. Here you can see we have started at A, then we have ended at A vertex also. So this is a Euler circuit. So that's how the Fleury's algorithm works. Now we will see how we can implement this Fleury's algorithm in Java. Now we will see how we can implement this Fleury's algorithm using Java. Here you can see I have implemented the functions needed for this Fleury's algorithm. So let's go by each function and explain it one by one. So this remove edge function, what it's going to do is remove an undirected edge from the graph. First, it is going to remove v from adjacency list of u. Then after that, remove u from adjacency list of v. We are going to remove from both sides because this is undirected. And we are going to remove from value of u, not by the index. Then after that, we are going to go to DFS count function. This is going to be used to check all the reachable vertices from the given vertex. Here we are going to set v as true. Then after that, we are going to visit all the unvisited neighbors of this v. Then after that, is valid next. This is gonna be used to check if the edge uv is valid to take as next in Fleury's algorithm. So if this vertex only has one edge, it is going to be taken since this is the only option. If not, we are going to check whether this edge is a bridge edge or not. So how we are going to do this is, first we are going to take the DFS count of this vertex to check whether to check how many vertices we can visit from this edge. From how many vertices we can visit. After that, we are going to remove this edge. Then after removing this edge, we are going to reset the visited values of u to 0. Then after that, we are going to take the DFS count again for count 2. Then we are going to add this edge again. Then we are going to check whether this count has changed. If not, if this count has changed, that means the reachability has changed. So this is a bridge edge. So we are not going to take that edge. Then we are the get util function. This is going to be used to build the Euler path. So first, this is going to go for all the neighbors of u. Check whether that get a starting adjacency vertex from u. Checks whether that edge is valid to be taken as the next edge. Then we are going, if it is valid, we are going to add it to the resulting edges. After that, we are going to remove that edge. Then we are going to recursively call for this function again with starting from the next vertex. Then the get Euler tool. This is going to be used to find the starting vertex of this algorithm. So at first we are going to start at index 0. If this contains an odd degree, we have to start from that vertex. Here it is done through this for loop. We are going to iterate to these all available indices. If any vertex contains an odd degree, here you can see if the degree is not divisible by 2, we are going to start from that vertex. Then here you can see we are going to call to get Euler util with the starting vertex as this vertex and the total v value. Then in the main function, here you can see I have taken the total vertices as 4 here, and in this I have created this graph with the total 4 vertices. Then after that, we are going to store the result in this rest list value. Then after that, we are going to print this result. So for this given graph, the output should be here starting from 2. Since this is a odd degree vertex, we have started from 2 and we have entered from 3. Since this is a Euler path, we are not going to be ending with the same vertex. Alright everyone, that's it for this video. I hope you got a solid understanding about what is Euler path, what is Euler cycle or circuit,
and what is an Eulerian graph, and what are the conditions we need to have for Euler path or a cycle, and how we can print an Euler path using Fleury's algorithm, and how we can implement it using Java. So if you have any questions or suggestions, please drop them in the comments. Thank you for watching this video, and I will see you in the next one.